Welcome back. We will discuss the rethinking data entry, storage, and retrieval. So it's more about how the database actually work in the background and how we can optimize it to our user interfaces. Um, rethinking data entry, storage, and retrieval. In the world of digital technology, the place where implementation model thinking is most strikingly apparent is that in data management. Entering data, storing it, and finding it again. How often have you typed information into a set of forms only to be told by an unpleasant or confusing error dialogue that you entered it wrong? Maybe you type hyphens in a telephone number, or perhaps you enter both your first and last name into the field that was intended to only hold your first name. So the reason for this is the design of the interface still implement the developer view of how computer actually works. The problem don't end with data entry. If you have ever tried to teach your mother how to use a computer, you will know that the word difficult doesn't really do the problem justice. Things go well at first. You start the word processor and type a couple of sentences. First, she's with you all the way, like typing on paper. But when you click the close button, up pops a dialogue asking, "Do you want to save changes?" You and mom hit a wall together. She looks at you and asks, does this mean? Is everything okay?" And once you've talked her way down and she performed the save, she has one more pressing difficult question. Where did it go? And how will I ever be able to find it again? Or it might even be on your own smartphone. You want to show an awesome photo to a friend, but given the long tapestry of thumbnails, have to spend more time hunting than the moment was really worth. So these things comes up naturally because of navigation constraints of the phone, and the interface was not really designed to meet the user goals. So we will rethink this data management, especially entering that data, storing it, and then finding it again. We will design the application that suit the mental model of our user. And then we will remove this dialogue when we enter the wrong information. We will make sure that the user of our application will enter the right information. Um, we will avoid this having error of typing hyphens in a telephone number, or entering both first and last name into the field that was intended to only hold your first name. These problems are caused by software that forces people to think like computers by unnecessarily confronting them with the internal mechanisms of data entry, storage, and retrieval. So, develop implementation model is basically and for developer enforcing their way of seeing the data entry, storage, and retrieval to the customer's mental model. So they are forcing them to be developer or use the interface. This is isn't just a problem for your mother. Even sophisticated users can easily become confused or make mistakes. This chapter provides a different set of approaches for taking the problems of data entry, files and saving, and retrieval, ones that are more in harmony with the mental models of the people who use your products. So mainly we will tackle data entry, files, and saving and retrieval. So I know a lot of you don't know the files yet, but we will discuss some of the back end and front end so that we can have a holistic understanding of it. Rethinking data entry. Some unfortunate artifacts of implementation model thinking prevent people from working in the way they find most natural. In this chapter, we'll discuss problems with existing ways of dealing with data entry and some possible strategies for making this process more focused on human needs and less focused on the needs of the database. Data integrity versus data immunity. All data is validated at its point of entry. Anything on the outside is assumed to be suspect, and after it has run the gauntlet and been allowed inside, it assumed to be pristine. The advantage is that once data is inside the database, the code doesn't have to be bothered with successive repetitive checks of its validity or appropriateness. You don't come across this problem with most mobile or personal productivity software. PowerPoint doesn't know or care if you formatted your presentation correctly. But as soon as you deal with a large corporation, whether you are a clerk performing data entry for an enterprise management system or web surfer buying DVDs online, you come to face with border patrol. So if you are a knowledge worker using an application, software application, you probably come into this issue of database because the developer doesn't want to do the hard work at the back end. So they want you to validate the data that you are putting. But as we will later see, humans are prone to mistakes, so the developer must do the hard work instead. People who fill out lots of form every day as part of their job know that data typically isn't provided to them in the pristine form that their software demands. It is often incomplete and sometimes wrong. So a lot of times, people doesn't actually know their search beforehand. So it's illogical for you to expect that software will understand or know that user will know what they would search because they often have incomplete information and they often have make mistakes. It's just the way their mind works. Furthermore, they may break from a form's strict demands to expedite this data processing to make their customer happy. So they may break the demand of the form to expedite this the data processing for their customer to be happy. So they will actually find a way to break that software rules. But when confronted with a system that is entirely inflexible in such matters, these people must either grind to a halt or find some way to subvert the system to get things done. Instead of keeping it out of the system, the developer needs to make the system immune to inconsistencies and gaps in the information. This method involves creating much smarter, more sophisticated applications that can handle all permutations of data, giving the application a kind of data immunity. Yes, if the user enters ASDF instead of 9.38, the application will be unable to achieve satisfactory results. But stopping the application to resolve this right now also is unsatisfactory. The entry process is just as important as the end report. So, stopping it in the entry is as unsatisfactory as the end report. If a user interface is designed correctly, the application provides visual feedback when the user enters ASDF. So, it's very unlikely that the user will enter hundreds of bad records. So, if the user knows immediately using a rich visual feedback that allows us to see it before it happened, the user will avoid having that bad records. Generally, users act stupidly only when the application treat them stupidly. Handling missing data. The data entry clerk who fails to key in something as important as an invoice amount creates a real problem. However, it isn't necessarily appropriate for the application to stop the clerk and point out this failure. Think of your application as being like a car. Your users won't take kindly having the steering wheel locked up because the car discovered it was low on windshield washer fluid. Instead, application should provide more flexibility. Users may not immediately have access to data for all the required fields, and their workflow may be such that they first enter all the information they have on hand and then return when they have the information needed to fill in the other fields. So you must design your software in a way that they can enter the information they have and not close the session or the web application or desktop apps so that they can fill in on it later. Or you must provide a way for them to continue without inputting all the required all the information, or having as minimal data as possible that you could accept so that you could continue and process the request as soon as possible. Of course, it should be based on users' goal, based on goal-directed research. Of course, we still want our users to be aware of any required fields that are missing information, but we can communicate this to them through rich modeless feedback rather than stopping everything to let them know something they may be well aware of. The application should also help him. Data items such as part numbers that must be valid shouldn't be entered into free text fields. So a data item such as part number that must be valid shouldn't be entered in the text field control, because as we saw in the previous video, it's for a text, but instead should be entered via type ahead, auto completion fields, or bounded controls such as drop downs. Addresses and phone numbers should be entered more naturally into smart text fields that can parse the data. Most of our information processing systems do tolerate missing information. A missing name, code, number, or price can almost always be reconstructed from other data in the record. So this actually, a name, code, number, or price, as we will later see, could be reconstructed using other properties in the back end that will help the user autocomplete it or make it complete instead of making the user do the work of entering all the information. If not, the data can always be reconstructed by asking the various parties involved in the transaction. The cost is high, but not as high as the cost of lost productivity or technical support centers. Our information processing system can work just fine with missing data. Some developers who build the systems may not like all the extra work involved in dealing with missing data, so they invoke data integrity as an unbreakable law. As a result, thousands of clerks must interact with rigid, overbearing software under the false rubric of keeping database from crashing. Data entry infudgeability. If system is too rigid, it can't model real-world behaviors. A system that rejects the reality of its users is not helpful, even if the net result is that all its fields are valid. So even if it's valid, if it's not flexible, it won't help to achieve the user goal. Fudgeability can be difficult to build into a computer system because it demands a considerably more capable interface. Our clerk cannot move a document to the top of the queue Unless the queue, the document and its position in the queue can easily be seen. The tools for pulling a document out of the electronic stock and placing it on the top must also be present and obvious in their functions. Fungibility also requires facilities to hold records in suspense. But an undo facility has similar requirements. So you can implement this using undo facility, which we will gonna discuss in this next section, preventing errors and informing decisions. Our clerk cannot move a document, the tools for pulling a document out of the electronic stock and placing it on top must also be present and obvious in their functions. So you should must provide visual feedback, which we will discuss later. The best strategy to avoid abuse is using the computer's ability to record the user's action for later examination, if warranted. The principle is simple. Let users do what they want, but keep detailed records of those actions so that full accountability and recovery is possible. Auditing versus editing. It is certainly an application's duty to inform other applications when they make an error. But this rule shouldn't necessarily extend to users. The customer is always right, so an application must accept what the user tells it, regardless of what it does or doesn't know. Humans make mistakes and your users are no exceptions. User errors may not be your application's fault, but they are its responsibility. How will it fix them? Design principle: an error may not be your application's fault, but it is its responsibility. Warning should clearly and modelessly tell users what they have done, much as the speedometer silently report are speed violations. It is unreasonable, however, for the application to stop the proceeding, just as it is not right for the speedometer to cut the gas when we edge above 65 miles per hour. Instead of an error dialog, for example, data entry fields can highlight any user input in the application. Highlight any user input the application evaluates a suspect. Our application should, however, remember each of the user's action and ensure that each action can be cleanly reversed, that no collateral information is lost, and that user can figure out when the application thinks the problems might be. Essentially, we maintain a clear audit trail of his actions. Design principle: audit, don't edit. So, all the user's input is valid. Don't edit it automatically out of for the users. The user know what he or she is doing. Let them audit it if they want to change it later. Have an undo facility, etc. Microsoft Word as an excellent example of auditing, as well as a nasty counterexample. This excellent example is how it handles real-time spell checking. As you type, red wavy underlines identify words that the application doesn't recognize, as shown in figure 14.1. Right-clicking these words pops up a menu of alternatives you can choose from. But you don't have to change anything, and you are not interrupted by dialogues or other forms of modal idiocy. Figure 14.1, Microsoft Word's automatic spell checker audits misspelled words with a wavy red underline, giving users modeless feedback. Right-clicking an underlined word pops up a menu of possible alternatives to choose from. This design idiom has been widely copied by both desktop and mobile apps. Word's autocorrect feature, on the other hand, can be a bit disturbing at first. As you type, it silently changes words it thinks are misspelled. It turns out that this feature is incredibly useful for fixing minor typos as you go. However, the corrections leave no obvious audit trail, so the user doesn't realize that what he typed has been changed. It would be better if Word could provide some kind of mark that indicates it has made a correction on the off chance that it has miscorrected something. This possibility becomes much more likely if, for instance, you are writing a technical paper heavy in specialized terminology and acronyms. However, it also violates the audit don't edit because it automatically changed the word and it doesn't provide a rich modeless feedback on what word has been changed. More irksome is word auto format feature, which tries to interpret user behavior like use of asterisk and numbers in text to automatically format number list and other paragraph formats. So this words auto format feature, like when you write a number in text, it will automatically format to a numbered list. So in the back end, it actually used an algorithm for list and other paragraph formats. When this works, it seems magical, but frequently the application does the wrong thing. And once it does, there's not always a straightforward way to undo the action. Auto format tries to be just a bit too smart. It should really leave the thinking to humans. Luckily, this feature can be turned off, and Word provides a special in-place menu that allow users to adjust auto format assumptions. In real world, humans accept partially and incorrectly filled in documents from each other all the time. We make a note to fix the problem later, and we usually do. If we forget, we fix the omission when we eventually discover it. Even if we never fix it, we somehow survive. Rethinking data storage. In our experience, people find computer file systems, the facilities that store application and data files on disk, difficult to use and understand. This is one of the most critical components of computers, and errors here have significant consequences. The difference between main memory and longer-term storage is unclear to most people. The popularization of web applications and other database-driven software has been a great opportunity to abandon this baggage of computer file system implementation model thinking. So web applications are actually the start where you immediately are integrated to the cloud or database somewhere. But for desktop applications before, it's just mainly a code that is downloaded to your operating system such as Windows, and it doesn't really have that cloud capability. As mentioned before, Google has led the charge with cloud-based web apps that autosave, sparing users the worry and confusion. Mobile operating system like iOS try to address the problem of storage by tightly associating documents with the application that created them. You need to open the application to access the set of documents you created using it. So the iOS actually for iPhone, they try to address the problem of this implementation model or storage, thinking of developers by associating the documents with the application that created them. So the application actually have the documents that they used on the iOS. You need to open the application to access the set of documents you created using it. Documents are saved automatically and also are retrieved from within the application. So just like Google, they save that automatically, and then you can retrieve that within the application. This makes things a lot simpler once you get used to the app-centric paradigm, until you need to work on your document with a different application. So if you're using a different application on iOS, it will collapse because it's hard to connect it. It's not related, since the document was integrated to the app, not on the phone itself. The iOS break this tight association rule with only a few document types, like photos, for example. So any app that capture photos break that association rule, which means other app could use the photos, but for other file types, it is interlinked with the app. So the privacy, etc. Since Apple is already is also concerned with privacy a lot, and then you are back to hunting for the one you need in a set of containers. The problems with data storage, technically speaking, every running app really exists in two places at once: in memory and on disk, or flash storage on mobile device. So basically, every app exists in two places: in the memory of your computer or mobile phone, and on the disk or SD card, or flash storage on mobile device. The same is true of every open file. So it's the same with open file, any photos or file types that you see on your computer. For the time being, this is a necessary state of affairs. Our technology has different mechanisms for accessing data in a responsive way: dynamic RAM memory, and storing the data for future use for disk or flash memory. So they store that data in disk for future use, but for current use, it's stored in memory. However, this is not what most people think is going on. Most of our mental models, aside from developers, are of a single document that we are directly creating and making changes to. Unfortunately, most software present us with a confusing representation of the implementation model of data storage. So most people actually think of that as a single document that we manipulate, or single app that we manipulate on the computers. They don't think that as two instances of the same file. That's why it creates a confusion on user mental model. Saving changes, when a save changes dialog like this one in figure 14.2 opens, users suppresses a twinge of fear and confusion and click the save button out of habit. A dialog that is always answered the same way is redundant and should be eliminated. Figure 14.2. This is the question word asked when you close a file after you have edited it. This dialog is a result of the developers inflicting the implementation model of the disk file system on the helpless users. This dialog is so unexpected by new users that they often choose don't save inadvertently. So after they edit, they should choose do a save, right? They want to save changes you made. The application could have expected and provide the reasonable judgment that the user, of course, after hours of editing, wants to save it. The application launches the save changes dialog when the user requests close or quit. So it's actually named save changes dialog when the user requests close or quit, because that is when it has to reconcile the difference between the copy of the document in memory and the copy on the disk. So right now that edit document is on the memory. If the user want to save it, if the user close the document and the user want to save it in the disk or for long term, he needs to click save. But in most cases, querying the user is simply unnecessary and a yes can be assumed. So the save changes dialog is based on a poor assumption that saving and not saving are equally probable behaviors. The dialog gives equal weight to these two options, even though the save button is clicked orders of magnitude more frequently than the don't save button. So, the application mistaken the probable the possibility and probability. So it didn't research the user appropriately, because the most probable behavior is to save it. The dialog gives equal weight to these two options, even though the save button is clicked orders of magnitude more frequently than the don't save button. As we discussed in chapter 11, this is a case of confusing possibility and probability. The user might occasionally say don't save, but the user almost always will say save. Mom is thinking, if I didn't want those changes, why would I have closed the document with them in there? To her, the question is absurd. In reality, many applications need not concern themselves with document or file management. Apple's iPhoto and iTunes both provide rich and easy to use functionality that allows a typical user to ignore the fact that a file even exists. In iTunes, so because the file exists in two ways, memory and disk, Apple's iPhoto and iTunes provide a rich and visual functionality and easy to use that allows them to the users to ignore the fact that the file or that concept exists. In iTunes, a playlist can be created, modified, shared, put onto an iPad, and persist for years. So it's automatically save it on the disk without the user even having to worry about the dialog box each time he creates something, modified, shared a music, even though the user has never explicitly saved it. Similarly, in iPhoto, image files are sucked out of camera into the application and can be organized, shown, emailed, and printed. So in iPhoto, image files are sucked out of camera into the application. It can since it is saved on the disk, you have an option or function to organize it, shown, email, and printed, all without users even thinking about the file system. And mobile devices running iOS and Android have largely eliminated the concept of explicit saving. That's why we use the phone almost automatically or seamlessly. Closing the documents without saving. If you've been using computers for a long time, you've been conditioned to think that the document close function is the appropriate way to abandon unwanted changes if you make an error or are simply nodding around. This is incorrect. The proper time to reject changes is when the changes are made. So, since it automatically changed, once you close that or hit the X button, the documents are actually saved already. That's how the app should work. Not that it won't save it when you exit because you've done a lot of work. We even have a well-established idiom to support this, the undo function. So, you should assume again to save this, and then if not, you can use an undo function. What's missing is a good way to perform a session level undo, such as the revert function, which only a few applications like Adobe, Photoshop support. So what's missing is like a session. When you open a session or a window, you can undo or revert it, or all the changes will be made automatically to the disk. And then if you don't want to change it, you can undo it, because that data is automatically saved in a file somewhere on the system. So that's how the desktop connected to the operating system works of Windows, such as Microsoft Word. Which only a few applications like Adobe Photoshop support without resorting to closing the document without saving. So once you close, it automatically save on modern application. Experienced user also learn to use the save changes dialog for similar purposes. Since there's no easy way to undo massive changes in most documents, we misuse the save changes dialog by choosing don't save. Since there is no easy way to undo massive change, since it's stored in memory in most documents, we misuse the save changes dialog by choosing don't save. So if you discover yourself making big changes to the wrong file, you use this dialog as a kind of escape valve to return things to the status quo. So people are confused back then because they choose don't save to return to the previously edit document instead of using just an undo function to revert back to the previous state of the document. This is handy, but it's also a hack. As we just mentioned, you have more discoverable ways to address this problem. Later, we will discover how we can actually solve this issue. Save as, what you save, when you save a document for the first time or choose the save as command from file menu, many applications display the save as dialog, which shouldn't be, because it should assume that when you hit Ctrl S or save, it should save the document, because you've again made a lot of work. Figure 14.3, the save as dialog provides two functions. It lets you name your file and it lets you place it in a directory you choose. Users, however, don't have a clear concept of saving, so the title of the dialog does not match their mental models of the function, so it does not match on how they understand save. So this dialog, the save as doesn't mean anything for them. Furthermore, if a dialog allows you to name and place a document, you might expect it to allow you to rename and replace it as well. Unfortunately, our expectations are confounded by poor design. Functionality, this dialog offers two things. It lets users name a file, and it lets them choose which directory to place it in. Both of these functions demand that the user have intimate knowledge of the file system and a fair amount of foresight into how they'll need to retrieve the file later. So because this dialog lets user name a file, and then it also let them choose the directory, kind of like how the developers see a file system or how they create an application. It demands users that intimate knowledge. So users must know how to formulate an acceptable and memorable file name and understand the hierarchical file directory. Many users who master the name portion give up on trying to understand the directory tree. So once they understand this, how to change name, they give up on how to understanding this directory, such as libraries or documents or inside libraries, etc. They put their documents on their desktop or in the directory that application chooses as a default. Occasionally, Some action causes the application to forget its default directory. And these users must call in an expert to find their files because the application revert or change how they save the files in the default directory. If it's to name and place files, it does a very poor job. After the user has named and placed a file for the first time, he cannot change its name or directory without creating a new document. At least not with this dialog, which purports to offer naming and placing functions. So they think that the user thought that he can change the name or the directory name using those dialog because that's what it purports to do, but it only meant for a new document name to be saved. Nor he can he do so with any other tool in the application itself. So usually that's F2 for Windows to change name, but after you have saved the document. In fact, in Windows 7, he can rename other files using this dialog. But not the ones he is currently working on. So actually, that using that dialog before could be used to change other files, but not the uh, document currently in the working memory. Huh? Beginners are out of luck, but experienced users learn the hard way, that they can close the document, launch Windows Explorer app that allows them to manage the file, rename the file. So Windows Explorer is where all the files save on the disk. So remember, all these things that we open on the document is actually in memory. So it launched the Windows Explorer, rename the file using the rename modal box, right click, return to the application, summon the open dialog from the file menu, and reopen the document from the file explorer or from the disk. Forcing the user to go to Explorer to rename the document is a minor hardship, but therein lies a hidden trap. The bait is that Windows easily supports several applications running simultaneously. Attracted by this feature, the user tries to rename the file in the Explorer without first closing the document in the application. So I know you've experienced this, where you try to rename a currently open file, and the Windows will ask you to close the file before you can edit it, because that document is just running in the memory, not in the disk, and also it's currently being edited. So anything that might change there could hinder the renaming. That's why the Windows wants you to change it. So this very reasonable action triggers the trap, and the Steel Jaws clamp down hard on his leg. He is rebuffed with the root error message back shown in figure 14.4. So if the user attempts to rename a file using Explorer while Word is still editing it, Explorer is too stupid to get around the problem. It also too rude to be nice about it and puts up this patronizing error message. Rebuffed by both the editing application and the OS, a new user might conclude that a document cannot be renamed. So the new users, especially older people, may think that this file could not be renamed. Trying to rename an open file is a sharing violation. So if you rename an open file, is actually a sharing violation in the Windows security policy, and the operating system rejects it with a patronizing error message. So the innocent user is merely trying to rename his document, and he finds himself lost in operating system Arcana. Ironically, the only entity that has both the authority and the responsibility to change the document's name while it is still open, the application itself refuses to even try. So the application actually has the responsibility, not the operating system. So the application should be able to actually rename the file, not the operating system security, not be condemned by operating system security policy. Archiving, there is no explicit function for making a copy of or archiving a document. So there's actually no clear function for making a copy of a document. So archiving is like making a copy. Users must accomplish this with save as dialog, and doing so is as clear as mud. If the user has already saved the file as alpha, she must explicitly call up the save as dialog and change the name. Alpha is closed and put away on disk, and new alpha is left open for editing. This action makes very little sense from a single document viewpoint of the world, and it also presents a nasty trap for the user. So if you already saved the alpha, you must open the save as dialog again and change the name. And alpha is closed and put away on disk. However, that alpha document will be removed if you do that using save as dialog. It doesn't actually make a copy. I know you guys should just copy and paste in desktop, but for Word, actually it works differently. A new alpha is left open for editing. So that new document, the new alpha, will be a completely new document instead of a copy of the alpha document. So this action makes very little sense from a single document viewpoint of the world. So if the user are not a developer, he or she is thinking that it's just a one document. Here's a completely reasonable scenario that leads to trouble. Suppose our user has been editing alpha for the last 20 minutes and now wants to make an archival copy of it on the disk so that she can make some big experimental changes to the original. She calls up the save as dialog and changes the file name to new alpha. The application puts away alpha on disk, leaving her to edit new alpha, but alpha was never saved, so it gets written to disk without any of the changes. She made it in the last 20 minutes. Those changes only exist in the new alpha copy that is currently in the memory in the application, because that's what she is currently editing. As she begins cutting and pasting in new alpha, trusting that her handiwork is backed up by alpha, she is actually modifying the sole copy of this information. Everybody knows that you can use a hammer to drive a screw or pliers to bash in a nail. But any skilled craftsperson knows that using wrong tool for the job will eventually catch up with you. The tool will break or the work will be ruined. The save as dialog is the wrong tool for making and managing copies, and it is the user who will eventually have to pick up the pieces. Fixing data storage, a unified file model. Properly designed software should treat a document as a single thing. So fixing this model of file system or implementation model should treat a document as a single thing, never as a copy on disk and a copy in memory. In this unified file model, users should never be forced to confront the computer's internal mechanism. It is the file system job to manage the writing data between the disk and memory. The established standard suite of file management for most applications includes open, save, and close commands. and the related save as, save changes, and open dialogues. So since this is a standard suite, it should complement with a standard model. So since open, save, and close command of the file are the standard suite of icon in menu, it must follow that user mental model of single document. Collectively, these dialogues, as we've shown, are confusing for some tasks and are completely incapable of performing other tasks. The following section describe different approach to document management that better support most user mental models. So this set of dialogues, as we've shown, are confusing for some tasks and are completely incapable of performing other tasks. The following sections describe a different approach to document management that better support most users' mental models. The user may need to perform several goal-directed tasks on document. Each one should have its own corresponding function. Automatic save, creating a copy, naming, and so this actually the user will perform a goal oriented depending on their goals on the goal directed research we've done. So they will do this on the document. So each one of these should have its corresponding function. Automatic save, creating a copy, naming and renaming, placing and repositioning in the file system, specifying the file type, reversing changes, discarding all changes, creating a version, communicating status. Automatic save, one of the most important functions every computer user must learn is how to save a document. Invoking this function means taking whatever changes the user has made to the copy in computer memory and writing them to the disk copy of the document. So once we hit Ctrl S and save, it actually saves it from memory to the disk. In the unified model, we abolish all user interface recognition of the two copies. So the save function disappears from the mainstream interface. So that doesn't mean it disappears from the application. It's still a necessary operation. Design principle, save documents and settings automatically. So you must save it. For starters, when the user is done with the document and requests the close function, the application should go ahead and write the changes to disk without stopping to ask for confirmation with the save changes dialog. If the power fails before you save, all your changes are lost as the memory containing them scrambles. The original copy on disk will be alright, but hours of work can still be lost. To prevent this from happening, the application must also save the document at intervals during the user session. So to prevent that power lost in memory, the application must automatically save it on interval. So it must be programmed to do that. It is important that this automatic save functions does not affect the responsiveness of the user interface. Saving should be either a background process, like a daemonic application we've discussed in the previous video, or performed when the user has stopped interacting with the application. Nobody types continuously, everybody stops to gather his thoughts, or flip a page, or take a sip of coffee. All the application needs to do is to wait until the user stops typing for a couple of seconds and then save. However, people who have been using computers for a long time are so paranoid about crashes and data loss that they habitually press Ctrl plus S after every paragraph and sometimes after every sentence. Applications serving this user should have manual save controls. So if you're saving expert user, you should have a manual save controls for your application, like Ctrl S for Word. But users should not be required to invoke manual saves. So the application must done them for the to better serve them. Creating a copy, there should be a function, expression function called create a copy. The copy will be identical to the original, but it won't be tied to the original in any way. That is, subsequent changes to the original will have no effect on the copy. If an existing document already has that name, the new copy should be named alpha copy 2. The copy should be placed in the same directory as the original. So the default should be copy on the same directory of the original. A nice option might be to add a time or date timestamp at the end of the file name. So another property or objects that you could implement in this function is a timestamp and end of date of the date stamp at the end of the file name. At the end of the file name, there should be a date stamp property. It is tempting to envision a dialog that accompanies this command, but there should be no such interruption. So there should be no interruption in this dialog, such as in Control C and Control V in desktop of any file, right? The application should take its action quietly, efficiently, and sensibly without badgering the user with silly dialogues like, "Are you sure you want to make a copy?" In the user mind, it is a simple command. Naming and renaming. In most applications, when you save a document for the first time, you can choose a name for it, but almost no application lets you rename that file. Sure, you can save as under another name, but that just makes another file under the new name, leaving the old file untouched under the old name. Sure, you can save as under another name, but that just makes another file under the new name, leaving the old file untouched under the old name. So if you use another name in this save as dialog, you actually create a new file instead of renaming that file. So you should create an option in the dialog or somewhere to rename it. So the document's name should be shown on the application's title bar. If the user decides to rename the document, he should be able to click the title to edit it in place. What could be simpler and more direct than that? So figure 14.5 OmniGraffle on OS X supports rename. Clicking on the name of the file in the title bar of the document windows open a pop-up that lets you both rename and move the file. So if you click the title in this OmniGraffle on the title bar of the document beta, it will open a pop-up that lets you both rename and move the file like this. So it allows you to move the file into the different directory as well. So that's a great dialog box. Placing and positioning in the file system. Most often, when someone uses an application to edit a document, that document already exists. Documents are typically opened rather than created from scratch. So usually, a document are opened rather than created from scratch. This means that their position in the file system is already established. Though we could think of directory where we want to save it, it's still the implementation model. The new file should be put somewhere reasonable where the user can find it again, like desktop, not the app local directory. So you should put the files in the desktop instead of the common app directory of the common desktop window. So design principle, put files where users can find them. The specific appropriate location should depend on your user and the posture of the product you are designing. For complex sovereign applications that most people use daily, it is sometimes appropriate to define an application-specific document location. But for transient application or sovereign application that are used less frequently, don't hide your user's files in your own special corner of the file system. If the user wants to place the document somewhere else, he can request this function from the menu. So if the user wants to place it in the app directory, you must provide an option in the menu to do that. So a move dialog would then appear with the current document highlighted using that menu, or move dialog box. If you open that with the current document, it will be selected. In this dialog or modal dialog, an appropriately named relative of the save as dialog, the user could move the file to any location. So it's like a save as dialog. So the application thus would place all files automatically, and this dialog would be used only to move them elsewhere. So this dialog are only function are to move the file elsewhere. Specifying the file type. At the bottom of the current save as dialog shown in figure 14.3, a combo box allows the user to specify a file type. So here there's actually a combo box like save as type here that allows you to choose what noun or what file type it will be applied when you hit the save command. It will allow you to apply that function. This function should not be located here for most applications. When the type is tied to the act of saving, additional unnecessary complexity is added to saving. In Word, if the user innocently changes the type, both the save function and any subsequent action are accompanied by a frightening and unexpected confirmation box. So in a word, if the user innocently changes the type, both the save function and any subsequent close action are accompanied by a frightening and unexpected confirmation box. So when you change the file type and hit, there is actually a confirmation box that will pop up to ask you if you're sure to change the file type. Overriding a file's type. A file's type is a relatively rare occurrence. So saving a file is a common occurrence. So these two functions should not be combined. Since that this is a rare function, it should not be combined in your application. From the user's point of view, the document type, rich text, plain text, or Word, for example, is a characteristic of document rather than of the disk file. So it's actually a characteristic of the document, like .doc or .pdf, not actually the what the disk see it when you save it. So specifying the type shouldn't be associated with the act of saving the file to disk. It belongs more properly in document properties dialog to change the properties of the document, accessible near the display of the document's file name. So it should be accessible on near the document's file name, like right-click modal dialog property. So this dialog should have significant cautions built into its interface to make it clear that the user that the function could involve significant data loss. In the case of some drawing applications, where saving image files as multiple types is desirable, An export dialog, which most drawing application already support, is appropriate for this function. So for drawing application where multiple types of that document is needed, an export dialog box is more appropriate. Reversing changes: if the user inadvertently makes changes to the document that must be reversed, a tool already exists for correcting these actions. Undo. So later we will discuss different types of undo, whether it's single undo, multiple undo, and redo as well. So the file system should not be called in surrogate for undo. A file system may be the mechanism that supports that the function. So you should not call the file explorer or the file manager for undo function. So the file system may be the mechanism that supports the function of undo, but you should not need two-step to call undo. Just a control Z is enough, or an icon near the document, but that doesn't mean it should be rendered to users in those terms. The concept of going directly to the file system to undo changes undermines the undo function, because you need to put a lot of steps. The version function shows a file-centric vision of undo can be implemented so that it works well with the unified file model. So a version function, in addition to the file system, to implement the undo, will provide a better, a closed way to fill the user mental model. Discarding all changes. Discarding all changes is not the most common task, but we want to allow the user to discard all the changes she made after opening or creating a document. Rather than forcing the user to understand the file system to achieve her goal, a simple discard changes function on the main menu. So there should be a main discard changes function, or like an icon, would suffice, or dialog box. A similar useful way to express this concept is revert to version. So since we already applied that revert version system, we could apply this function revert to version, which is based on version system. Because discard changes involve significant data loss, the user should be protected with clear warnings. This is where the confirmation dialog is appropriate. Making this function undoable also would be relatively easy to implement and highly desirable. So if you you can also disable this discard all changes, because again, user wants to save it. So, and you have a lot of disk space now, so there's no reason not to save all or everything. But if the user really need it, you can provide that confirmation. Creating a version. Creating a version is very similar to using the copy command. The difference is that this copy is managed by the application and presented to users as the single document instance after it is made. So actually, when you copy a file in the file system in desktop, you actually mimic how the application create a version. So the application present you an instance of the document, or a single document instance after it has made that version. It should also be clear to users that they can return to the state of document at each point that a version was made. So essentially, you're creating a different version when you're doing the undo. Like there's a copy or a snapshot of each document, how the document look like and all the data in each step So the application actually do that instead of the file system. Uh, Users should be able to see a list of versions along with various statistics about them, like the time each was recorded in its size or length. So like in GitHub, where you see all the timestamp and the size of that file, the user should also see that, and it actually implemented using statistics in the backend. With a click, the user can select a version. By doing so, he also immediately select it as the active document or the active main content of the application that he will manipulate. The document that was current at the time of the version selection will be created as a version itself. So the document that was current at the time of the version selection will be created as a version itself. So when you click that active version, it will be created as another version, like a copy of that version for you to manipulate. Also, since disk space is hardly a scarce resource, these days it makes sense to create versions regularly in case it doesn't occur to your users. So the application must have a functions or a background application that allows them to save the version automatically, since disk is hardly a scarce resource nowadays. So a new file menu now looks like the one shown in figure 14.6 when we apply all those principles. It functions as follow. The revised file menu now better reflects the user's mental model rather than the developer implementation model. There's only one file and the user owns it. If she wants, she can make track or one-off copies of it. So she can create a version of it, rename it, discard any changes she made. Here, revert the version, abandon changes, so you can see. So he can create a copy she made or change the file type in properties. She no longer needs to understand or worry about the copy in RAM versus the copy on disk. Here, new and open work as before. So it's new and open function work as before. Closes and closes the document without a dialog or any other fuss of after automatically saving changes. So when you close, it will automatically save without a dialog. Rename or move brings up a dialog that lets the user rename the current file or move it to another directory. Create a copy creates a new file that is a copy of the current document. Print collects all printer related controls in a single dialog. Create version is similar to copy except that the application manages this copy by way of a dialog summoned by the revert to version menu item. So it manages the copy using a dialog summoned by the revert to version menu item. So here this is the revert to version menu item. So that dialog are from this revert to version when you create this create version. Abandon changes, discard all changes made to the document since it was open or created. Properties open a dialog that lets the user change the document type. Exit behave as it does now, closing the document and the application instead of another confirmation dialog. A new file of a new name for the file menu. Now that we are presenting a unified model of storage instead of the bifurcated implementation of disk and RAM, we no longer need to call the leftmost application menu the file menu. So here we don't need to show file menu because a reflection of the implementation model not the user's model. There are two reasonable alternatives. We could label Nabinu according to the type of documents the application processes. For example, a spreadsheet application might label its leftmost menu sheet. An invoicing application might label it invoice. Alternatively, we could give the leftmost menu a more generic label such as document. This is a reasonable choice for applications like word processors, spreadsheets, and drawing applications, but it may be less appropriate for most more specified niche applications. Conversely, the few applications that do represent the content of disk as files, generally operating system shells and utilities, should have a file menu because they are addressing files as files. Communicating status. If the system needs to show the user a file that cannot be changed because it is in use by another application, the file system should indicate this to the user. So showing the file name in red or with a symbol next to it if the other other application are using it. Along with a tooltip explaining the situation would be sufficient. So a new user may still get an error as shown in figure 14.4, but at least some visual and textual clues would show that the reason the error cropped up without actually opening it. So it saved the user time of opening it. Figure 14.4, if the user attempts to rename a file using Explorer while Word is still editing it. Not only there are two copies of all data files in the current model, but when they are running, there are also two copies of all applications. So there's not only two files, but there's actually two copies of the application, the Microsoft Word in memory and the Microsoft Word in the disk. So when the user goes to the Windows taskbar, Start menu, and launches his word processor, a button corresponding to Word appears on the taskbar. But if he returns to the start menu, Word is still there. From the user's point of view, he has pulled his hammer out of his toolbox only to find that hammer is still in there. So when you go to this taskbar on the Windows app or icon, it launches the word processor, and a button corresponding to Word appears on the taskbar. But if he returns to the start menu, Word is still there, but from the user point of view, he has pulled his hammer. This should probably not be changed. After all, one of the strengths of the computer is its capability to have multiple copies of software running simultaneously. So because you can actually run multiple copies of that applications in the memory from the disk, those should not be changed. But the software should help users understand this unintuitive action. The start menu could, for example, make some reference to already running application. Or when you click the word, it will open the already open application instead of instantiating new application. Time for a change. Relax. There is nothing terribly wrong with the implementation of our file systems. We simply need to hide its existence from users. We can still offer users all the advantages of that extra copy on disk without exploding their mental model. First, all users will become more effective if they aren't forced to spend effort and mental energy managing their computer's file system. They'll be more focused on the task at hand, and of course, they won't have to redo hours of work lost to a mistake in the complex chess game of versioning in contemporary operating systems. So they won't redo hours of work lost to a mistake in the in the versioning in temporary operating system, and they will be more focused on the task at hand in their instead of spending their mental energy managing their computer file system. Second, we can teach mom how to really use computers well. We won't have to answer her pointed questions about the interface inexplicable um, behavior. We can show her applications and explain how they allow her to work on the document. Upon completion, she can store the document on the disk as though it were a journal on a shelf. Our sensible explanation won't be interrupted by that save changes dialogue. Mom represents the mass market of digital product consumers who may own and use computers and other devices but who don't like them, trust them, or use them effectively. The last advantage is that interaction designer won't have to incorporate clumsy file system awareness into their products. We can structure the commands in our applications according to user's goal instead of the operating system's need. So you don't need to incorporate the file system to the products. You can structure the command in the application according to user's goals instead of OS needs. There will certainly be an initial cost as experienced users get used to the new idioms, but it will be far less than you might suppose. This is because these power users have already shown their ability and tolerance by learning the implementation model. For them, learning the better model will be no problem and there will be no loss of functionality. The advantage for new users will be immediate and significant. We computer professionals forget how tall the mountain is after we've climbed it. But everyday newcomers approach the base of this Everest of computer literacy and are severely discouraged. Anything we can do to lower the heights they must scale will make a big difference, and this step will tame some of the most perilous peaks. By thinking data retrieval, one of the most amazing aspects of modern world is the sheer quantity of information and media we can access within our applications, on our laptops and mobile devices, and via networks and the internet. But accompanying the boundless possibilities of infinite data access is a difficult design problem. How do we make it easy for people to find what they're looking for, and more importantly, find what they need? Luckily, great strides have been made in this area by Google with its various search engines and Apple with its highly effective Spotlight functionality in OS X. More on this later. But although these solutions point to some effective interactions, they really just scratch the surface. Google search may be very useful for finding textual, image, or video content on the web, but that doesn't necessarily mean that the same interaction patterns are appropriate for a more targeted retrieval scenario. As with almost every other problem in interaction design, we've found that crafting an appropriate solution must start with a good understanding of users' mental models and usage contexts. With this information, we can structure storage and retrieval systems that accommodate specific purposes. Storage versus retrieval. A storage system is a method of safely keeping things in a repository. It is composed of a container and tools necessary to put objects in and take them out again. So, a storage system is a method of safely keeping things in a repository, just like a shelf and a book. So, you have this container, the shelves, and then the tools. The shelves are probably put or in a wall, and on objects and take them out again, which is the book. A retrieval system is a method of finding things in a repository according to some associated value such as name, position, or some other attribute of the contents. So a retrieval system is like finding things on that storage system or in container using some associated value such as name, position, or some other attribute, but usually just name and location, right? The most basic. In the physical world, Storing and retrieving are inextricably linked. Putting in an item on a shelf, storing it, also give us the means to find it later, retrieving it, because we know the location. In the digital world, the only thing linking these two concepts is our faulty thinking. Computers, so this is another like mechanical age or the real world imposing. We're trying to mimic the how it we store it in real world to the computers. Computers enable remarkably sophisticated retrieval techniques if only we can break our thinking out of its traditional box. Digital storage and retrieval mechanism have traditionally been based on the concept of folders or directories. It's certainly true that folder metaphor has provided a useful way to approach a computer storage and retrieval systems, much as one would approach themselves or a physical object. So traditionally, digital products are represent their files as folders and directory, which is how developers see it. But as we discussed in chapter 13, the metaphoric nature of this interaction pattern is limiting. Ultimately, the sole use of folders or directories as a retrieval mechanism requires that user know where an item has been stored in order to locate it. So for example, the files are in the some application directory. You need to go to the C drive system and then find that specific application directory. So what if you don't know what name of the file you are looking for? Retrieval in the physical world, we can make own a book or hammer without giving it a name or permanent place of residence in our house. So we don't need to give that a name. A book can be identified by characteristics other than a name, a color or shape, for example. However, after we accumulate a large number of items that we need to find and use, it helps to be a bit more organized. Retrieval by location. It is important that our books and hammers have a proper place because that is how we find them when we need them without a name. We can just whistle. We can't just whistle and expect them to find us. We must know where they are, and then go there and fetch them. In the physical world, the actual location of a thing is the means of finding it. Remembering where we put something, its address, is vital to both finding it and putting it away so it can be found again. When we want to find a spoon, for example, we go to the place where we keep our spoons. We don't find the spoon by referring to any inherent characteristics of the spoon itself. So we can find that just as we do with computer. Like a small spoon, we need to know where the location. Similarly, when we look for a book, we either go where we left the book or we guess that it's stored with other books. So we remember anything that could allow us to find that based on our previous action, such as when we lost our keys, we remember the place that we've been to find the keys. We don't find the book by association. That is, we don't find the book by referring to its contents. In this model, the storage system is the same as the retrieval system in the physical world. Both are based on remembering location. They are coupled storage and retrieval systems. Index retrieval. Retrieval by location sounds pretty good, but it has a flaw. It's limited in scale by human memory. So, although it works for the books, hammers, and spoons in your house, it doesn't work for all the volumes stored in the Library of Congress, for example. So it works for the house because it doesn't have a lot of items, and at your house, it's limited by your memory because it's only a few items. In the world of books and paper on library shelves, we make use of classification system to help us find things. Every book is assigned a unique call number based on its subject. Books are then arranged numerically and then alphabetically by author's last name, resulting in a library organized by subject. So there's a call number based on its subject. So books are then organized numerically and then alphabetically. So number and then alphabet by author's last name, resulting in an organized by subject. So you can find it using that unique call number because it based on its subject, based on alphabetically by author's last name. The only remaining issue is how to discover the number for a given book. So you already have this unique call number based on the subject, and then you arrange that using that call number numerically and then alphabetically. How do you now find that number if you forgot that? Certainly nobody could be expected to remember every number. The solution is an index or a collection of records that allow you to find an item's location by looking up an attribute of the item, such as its name. So since the number that call number is insufficient, a name is included, or an attribute of the item, such as name, is the solution. Traditional library card catalogs provide lookup by three attributes: author, subject, and title. So once you find the subject, you then find the name of the author. And then you can find that because easily because the author is ordered or sorted using last name, and then the title or the another attribute, which is the name of the book. When the book is entered into the library system and assigned a number, three index cards are created for the book: the author, the subject, and the title, including all particulars and the Dewey decimal number. Each card is headed by the author's name, subject, or title. So those three cards that we pulled up are headed by author's name, subject, and the title. These cards are then placed in their respective indices in alphabetical order. So these cards with author name, subject, and title are now sorted in alphabetical order. When you want to find a book, you look it up in one of the indices and find its number or the call number that you're looking for earlier. You then find the row of shelves that contain books. So that's the index, the row of shelves that contain books with numbers in the same range as you target by examining signs. You're getting closer and closer by getting to the row of shelves that contain books with numbers in the same range. So you only got those, you're close to the number range, and then as you close to the target, you examine the signs. You search those particular shelves, narrowing your view by the lexical order of the numbers until you find the one you want. So you search for the shelves, narrowing your view by the lexical order of the numbers until you find the one you want. So that's how you find it in library. You physically retrieve the book. So you go there on the shelves by participating in the system of storage. But you logically find the book you want by participating in a system of retrieval. So you do two systems, physical or storage system and retrieval. The shelves and numbers are the storage system. So the shelves and the numbers in it are the storage system. So the shelves and the numbers are the storage system. The card indices, which is the author's name, subject, and title, are the retrieval system. So those are the attributes. So you search for location as well the indices. You identify the desired book with one and fetch it with the other. So you identify the book that you are looking for with one of the indices, and then fetch it with the other, or help the other to be once you get one of this attribute, you just use that to find the other attribute. and then you get all the attributes of that particular book. In a typical university or professional library, customers are not allowed into the stocks. As a customer, you identify the book you want by using only the retrieval system. So you're not actually allowed to go inside to find the book. The librarian then fetches the book for you by participating only in the storage system. So the book's unique number is the bridge between these two interdependent systems. In the physical world, both the retrieval system and storage system may be labor intensive, particularly in older non-computerized library. They are both inflexible. Adding a fourth index based on acquisition date, for example, would be prohibitively difficult for the library. So adding a fourth attribute for that retrieval system will be difficult to find because there's just a lot of attributes to look. Retrieval in the digital world. Unlike in the physical world of books, stocks, and cards, it's not very hard to add an index in the computer. So just like unlike that in the library where adding an attributes in that retrieval system would be so difficult, in a digital world, it's not very hard to add an index in the computer. Ironically, in a system where easily implementing dynamic associated retrieval mechanism is at last possible. So associative retrieval mechanism is and implementing dynamic of it is at last possible. We often don't implement any retrieval system other than the storage system. The issue is we actually don't apply this addition of index in the library in the digital world. So later we will discuss how we would implement it. If you want to find a file under this, you need to know its name and place. It's as if we went into the library, burned the card catalog, and told the patrons they can easily find it where they want by just remembering the letter numbers on the spines of the books. We have put 100% of the burden of file retrieval on the user's memory, while the CPU just sits there idling, twiddling its digital thumbs on billions of no operation instructions. So since our CPU could find that easily, now we put all the burden in the memory. So we went back to the storage system of the library where we want the computer to find it in its location. Although our desktop computers can handle hundreds of different indices or attributes, we ignore this capability and frequently have no indices at all pointing into the file store on our disk. So actually the solution is to put the indices on the file so that we can easily find the book. Later we will discuss that. Instead we have to remember where we put our files and what we call them in order to find them again. So we actually remember where we put that in the directory and what we call them in order to find them again. This omission is one of the most destructive backward steps in modern software design. This failure can be attributed to interdependence of files and the organizational systems in which they exist, an interdependence that doesn't exist in the mechanical world. So this failure is because of the interdependence of the files that does not exist in the mechanical world. That's why we do this in storage base in the computer instead of more advanced index retrieval in the library. Instead, we hand the user the storage system and call it a retrieval system. This is like handing him a bag of groceries and calling it a gourmet dinner. There's no reason to change our file storage systems. The Unix model is fine. Our applications can easily remember the names and locations of the files they have worked on. So they aren't the ones who need a retrieval system. It's for us human users. Digital retrieval methods. There are three fundamental ways to find a document in a digital system. You can find it by remembering where you left it in the file structure, positional retrieval. You can also find it by remembering its identifying name, identity retrieval. It should be noted that these two methods typically are used in conjunction. The term method, associative or attribute-based retrieval, or the indices in the library, is based on the ability to search for a document or file based on some inherent quality of the document itself. So based on some properties. So actually, in the real world, we find it, the retrieval such as in the house, like a hammer in yourself, by location, and through identity, such as this is a hammer, and this position retrieval. So it's like in physical world, this is also apply or interdependent in digital world. For example, if you want to find a book with a red cover, or one that discusses light rail transit system, or one that contains photographs of steam locomotives, or one that mentions Tudor Judah, you may use an associative method. The combination of position and identity provides the basis for most digital storage systems. By ignoring associative methods, we deny ourselves any attribute-based searching, so we must depend on human memory to recall the position and identity of our documents. So we rely on the human memory to find the position and identity, or what we want to find, such as hammer and the location in the shelves. User must know the title of the document they want and where it is stored to find it. For example, to find a spreadsheet in which you calculated the amortization of your home loan, you need to remember that you stored it in a directory called home, and that file was amort1. If you can't remember either of these facts, finding the document is difficult. Attributed-based retrieval system. For early graphical interfaces like the original Macintosh, a positional retrieval system almost made sense. The desktop metaphor dictated it. You don't use an index to look up papers on your desk. And precious few documents could be stored on a 144 kilobyte floppy disk. So the reason why we use this positional retrieval is because of the desktop metaphor, the old metaphor, and the low capacity disk. However, our current desktop systems can easily hold 5 million times as many documents. We continue to render our software's retrieval system in strict adherence to the storage system implementation model of the storage system. We ignore the power and ease of use of a system finding files that is distinct from the system for keeping files. An attribute-based retrieval system enables users to find documents by their contents and meaningful properties, such as when they were last edited. The purpose of this attribute-based retrieval allows us to do this. The application will be able to allow to do this if you coded it on the back end, such as the properties, the last name edited of the function, or etc. The purpose of such system is to provide a mechanism for users to express what they're looking for according to how they think about it. So according to their mental model or their memory. For example, a saleswoman looking for a proposal she recently sent to a client named WidgetCo could effectively express by saying, show me the Word documents related to WidgetCo that I modified and printed yesterday. So it's according to what she remembered based on her mental model. Of course, there's a lot of attributes that could be used to look at the same file. But the key here is that getting or coding that in the backend as much as possible, so any user or the target user could easily find it. A well-crafted attribute-based retrieval system also enables users to find what they're looking for by synonyms or related topics, or by assigning attributes to individual documents. So the organization part, or in the dialog box that we've discussed in the previous video, and the synonyms are actually the key here in finding these attributes or individual documents. The user then dynamically defines sets of documents having these overlapping attributes. So when the user defined the attributes, you remember the overlapping attributes that has that same attributes documents will pop up, and the user choices are minimized drastically. Returning to our saleswoman example, each potential client is sent a proposal letter. Each of these letters is different and is naturally grouped with the files persistent to that client. However, there is a definite relationship between each of these letters because they all serve the same function, proposing a business relationship. So here, for the saleswoman example, each potential client sent a proposal letter, right? So if each of these letters is different, of course, each of these documents different and is naturally grouped with the files pertinent to that client. However, there's also common theme on this. They are about proposing a business relationship. So if you've done the user research right, you would know that this is a key action. It would be convenient if the saleswoman could find and gather all such proposal letters while allowing each one to retain its uniqueness and association with its particular client. So a file system based on a place on its single storage location. So if you have a file system that has this properly crafted attribute-based searching on its single storage location, must necessarily store each document by a single attribute, client, or document type rather than by multiple characteristics. A retrieval system can learn a lot about each document just by keeping its eyes and ears open. If it remembers some of this information, much of the burden on users is made unnecessary. For example, it can easily remember certain things like the user that created or the users that contributed to the document. When the user are using Word, for example, they can sign in and the system will show who created the document, the device that created the document, the application that created the document. So if it's Word or if the application using laptop, basically it's just collecting statistics on the back end and then using that attributes to help the user search for it. The documents content and type, what documents for Word, it could be docs, could be PDF, which application last opened the document. So the operating system could also track that. The document size and whether it is exceptionally large or small. So you can also track that in your hard drive. Whether the document has been untouched for a long time, so whether it's open by the operating system or some operating system in the system, how long the document was last open, how much information was added or deleted during the last edit, if the document was created from scratch or cloned from another, if the document is frequently edited, if the document is frequently viewed but rarely edited, whether the document has been printed and where, how often the document has been printed and whether the changes were made to it each time immediately before printing, whether the document has been faxed and to whom, whether the document has been emailed and to whom. Spotlight, the search function in Apple OS X, provides effective attribute-based retrieval as shown in figure 14.7. Not only the user look for documents according to meaningful properties, but he can save these searches as smart folders. Doing so enables him to see documents related to a given client in one place. So you can create an attribute that allows you to organize that on a given client and all proposals in a different place. However, he would have to put some effort into identifying each proposal, such as because Spotlight can't recognize them. So the user could create an attribute that he could search for that typical client depending on the most easier search term for him. Spotlight, the search capability in Apple OS X, allows user to find document based on meaningful attributes such as the name, type of document, and when it was last opened. It should be noted that one of the most important factors contributing to Spotlight usefulness is the speed in which results are returned. This is significant differentiating factor between it and the Windows search functionality, because it's within the application, not on the operating system. It was achieved through purposeful technical design that indexes content during idle time. So it actually indexes or find the attributes of the content using the idle time that the document was open. So after you open this the document, the system automatically find an attributes that is useful for those using Spotlight search that it could use to identify the document, such as the file type, etc. So it doesn't rely on operating system to search it. So that's why it doesn't take long to search a document, unlike in this file manager in your Windows. An attribute-based retrieval system can find documents for users without users ever having to explicitly organize documents in advance. So you don't need to organize. That's why you don't need to organize the folders anymore. You can find any type of document you want depending on your memory or mental model, because you can easily search any file there. But there is also considerable value in allowing users to tag or manually specify attributes about documents. These allow users to fill in the gaps where technology can identify all the meaningful attributes. So you can tag it, such as the hashtag in Twitter, to be able to find documents or that you are looking for without relying on the meaningful attributes that OS Spotlight provide. It also allows people to define de facto organizational scheme based on how they discuss and use information. The retrieval mechanism achieved by such tagging is often called a folksonomy, a term credited to information architect Thomas van der Waal. So like a tweet hashtag, so it allows people to use the word or attribute based on how they currently talk about it. Folksonymies can be especially useful in social and collaborative situations. There they can provide an alternative to globally defined taxonomy. It is undesirable or impractical to force everyone to adhere to and think in terms of a controlled vocabulary. Good example of the use of tagging facilitate information retrieval include Flickr, Delicious, and the highly popular social sharing app Twitter. Figure 14.8, Twitter, whose hashtags have become part of mainstream culture, is the classic example of folksonomy that has achieved widespread adoption. Relational database versus the digital soup. Software that uses database technology typically makes two simple demands of its user. First, user must define the form of the data in advance. Second, user must then conform to that definition. There are also two facts about human users of software. First, they rarely can express in advance what they will want, just what as we see on the previous video. Second, even if they could express their specific needs, more often than not, they change their minds. So, the software must be flexible. And then you should not expect the user know in advance their search term. Organizing the unorganizable. Living in the internet age, we find ourselves more and more frequently confronting information systems that fail the relational database litmus. We can neither define information in advance nor reliably stick to any definition we might conjure up. In particular, the two most common components of the internet exemplify this dilemma. First, let's consider email. Whereas a record in a database has a specific identity and thus belongs in a table of objects of the same type, an email message doesn't fit this paradigm very well. So a record in a database has a specific identity. It and thus belong in a table of objects of the same type. So a record usually belong to this table of object on the same type, whereas email is not. We can divide our email into incoming and outgoing, but that doesn't help us much. For example, if you receive a piece of email from Jerry about Sally regarding the Ajax project and how it relates to Jones Consulting in your joint presentation at the board meeting, you can file this in the Jerry folder or the Sally folder or the Ajax folder. But what you really want is to file it in all of them. In 6 months, you might try to find this message for any number of unpredictable reasons, and you want to be able to find it regardless of your reason. Second, like an infinite, chaotic, redundant, and supervised hard drive, the web defies structure. Enormous quantities of information are available on the web, but its sheer size and heterogeneity almost guarantee that no regular system could ever be imposed on it. Even if the web could be organized, the method would likely have to exist on the outside because its contents are owned by millions of individuals, none of whom are subject to any authority, unlike records in a database. We cannot expect to find a predictable identifying mark in a record on the table. Problems with the database. All database records are of single predefined type. So you predefine the type of the database, all of the database and relational database, but it was just before, because there's a not relational database anymore. I would suggest like going back on my previous video for that. A record may present an invoice or a customer, but it never represents an invoice and a customer. A record may represent an invoice or a customer, but it never represents an invoice and a customer. Similarly, a field within a record may be a name or social security number, but it is never a name and a social security number. So a record may represent, or a field record may be a name or a social security, but it is never a name and a security number. It serves the vital purpose of allowing us to impose order on our storage system. However, it's not enough that email from Jerry is a record type of type email. Somehow we must also identify it as a record type Jerry, type Sally, type Ajax, type Joan Consulting, and type board meeting. We must also be able to add and change its identity at will, even if after the record has been stored. So we must be able to edit it in the database. So since that database is just representation of that data, we should also be able to do it. What's more, a record of type Ajax may refer to documents other than email messages, such as a project plan. So it's not just email, it could be a project plan as well. Because the record format is unpredictable, the value that identifies the record as pertaining to Ajax cannot be stored reliably within the record itself. This actually was solved by non-relational database. This directly contradicts how database work. Though database allow us to find and fetch a record by examining its contents and matching them against search criteria. For example, we search for invoice number 77329 or for the customer with the identifying string Goodyear Tire and Rubber. Yet this still falls for our email problem. If we allow users to enter the keywords Jerry, Sally, Ajax, Jones Consulting, and board meeting into the message record, we must define such field in advance. So if we want to search it, we must define that field in the record in advance. But as we've said, defining things in advance doesn't guarantee that the user will follow that definition later. He may now be looking for a message about a company picnic, for example, instead of those search terms. Besides, adding a series of keyword fields led you into one of the most fundamental and universal conundrum of data processing. If you give users 10 fields, someone is bound to want 11. The attributes-based alternative. So if a relational database technology isn't right, what it is? So the solution is to impose the attributes-based alternative on your applications. If users find it hard to define their information in advance as database require, is there an alternative storage and retrieval system that might work well for them? Again, the key is separating the storage and retrieval system. If an index were used as the retrieval system, the storage technique could remain a database. We can imagine that
storage facility as a sort of digital soup where we could put our records. This would accept any record we dump into it, regardless of its size, length, type, or contents. Whenever a record was entered, the application would return a token that could be used to retrieve the record. So the database or the application would return a token that could be used to retrieve the record. All we have to do is give it back that token, and the soup would instantly return our record. Because of safety, we need to give back the database the token. This is just our storage system. However, we still need a retrieval system that manages all these tokens for us. Attribute-based retrieval thus comes to our rescue. We can create an index that stores a key value along with a copy of the content. So here, the attribute-based retrieval, we actually create an index that store a key value along with a copy of the token. So there's a key, there's a value in the token from database. The real magic though is that we can create an infinite number of indices or key value, each one representing its own key and containing a copy of that token. So for example, if our digital soup contained all our email messages, we could establish an index each of our old friends, Jerry, Sally, Ajax, Jones Consulting, and board meeting. Now when we need to find email pertinent to the board meeting, we don't have to poll manually and tediously through dozens of folders. Instead, a single query brings us everything we are looking for. So we can actually create an index within our app with the different keys, Jerry, Sally, etc. Now when we need to find that email, we don't have to poll using an operating system all the folders in the database. Instead, a single query brings us everything we're looking for. Of course, someone or something must fill those indices. First, the system must be able to read images, email messages, and automatically extract and index information such as proper names, internet address, street address, phone numbers, and other significant data from that email. So that application could actually do that for that significant data. And then second, the system must make it very easy for the user to add an ad hoc pointers to the message. So this is where you fill those indices. He should be able to specify that a given email message pertains to a certain value, whether or not that value is coded verbatim in the message. So whether it's not coded in the email, the user mental model still follows. Typing is okay, but selecting from pick list or clicking and dragging and other more advanced user interface idioms can make the task almost painless. So just dragging what they want from pre-selected possible indices is all make this process almost painless. Important advantage arises when the storage system is reduced in importance and the retrieval system is separated from it and significantly enhanced. So there's an advantage when the storage system is reduced in importance, or the database, and the retrieval system is separated from it. Some forms of digital soup will help us get control of the unpredictable information that is beginning to make up more and more of our everyday information universe. We can offer users powerful information management tools without demanding that they configure their information in advance or that they conform to that configuration in the future. After all, they can do it, so why insist? We will get constrained natural language input. So there's another way to make the search easy. This chapter has discussed the merits of attributes-based retrieval. This kind of system, to be truly successful, requires a front end that allows users to easily make sense of what could be complex and interrelated set of attributes of keys and values in the record in the table in the back end. One alternative is to use natural language processing, in which the user can key in his request in English. The problem with this method is that it is still not possible for today's run-of-the-mill computers to effectively understand natural language queries in most commercial situations. So it's still not possible for the database to run natural language or English queries in most commercial situations. It might work reasonably in the laboratory under tight controlled condition or in the real world for specific domains with tightly controlled vocabulary and syntax, but not in the consumer world where language is subject to whim, dialect, colloquialism, and ambiguity. So if there's a structured system, this might work or just fixed language, but for this interconnected consumer, language are subject to change. In any case, the programming of a natural language recognition engine is beyond the capabilities and budget of your average development team. But ChatGPT is now here, so we don't know if it's still true. That statement still to a better approach, which we've used successfully in numerous projects, is a technique we call constrained natural language output. Using this technique, the application provides an array of bounded controls for users to choose from. So array of bounded controls that mimic how we speak the database. The controls line up so that they can be read like an English sentence. The user chooses from a list of valid alternatives, so the design in essence a self-documenting bounded query facility. Figure 49.9 shows how this works. An example of constrained natural language output interface on attribute-based retrieval engine or database, part of Cooper design created for soft text storage manager. These controls produce natural language as output rather than attempting to accept natural language as input. So it actually produced the output from the database as a natural language rather than attempting to accept natural language as input for database queries. So it make it the attribute retrieval reverse. Each underlined phrase, when clicked, provides a drop-down menu with a list of selectable options. The user construct a sentence from a dynamic series of choices that always guarantees a valid result. So it's like making the database query language English. A natural language output interface is also helpful for expressing everything from queries to plain old relational database. Querying a database in the usual fashion is very hard for most people because it calls for Boolean notation and arcane database syntax, a la SQL, or SQL. English isn't Boolean, so the English clauses aren't joined with and or, but rather with English phrases like all of the following apply or not all of the following apply. Users find that choosing from among these phrases is easy because they are clear and bounded, and user can read the phrase like a sentence to check its validity. The trickiest part of natural language output from development perspective is that choosing from controls on the left may in many circumstances change the content of the choice in controls to the right of them in a cascading fashion. This means that to effectively implement natural language output, the grammar of the choices needed to be well mapped out in advance. Also, the controls need to be dynamically changeable or hideable depending on what is selected in other controls. Finally, the controls themselves must be able to display or at least load data dynamically. The other concern is localization. If you are designing for multiple language, those with very different word orders, for example, German and English, may require different grammar mappings. Both attribute-based retrieval engines and natural language output interfaces require significant design and programming effort, but users will reap tremendous benefit in terms of power and flexibility in managing their data. Because the amount of data all must change is growing at an exponential rate, it makes sense to invest now in this more powerful goal-directed tools wherever data must be managed. So just take a break a little bit. We will continue with this. So just a moment. So we'll continue with rich modeless feedback that we've been talking since the beginning. So preventing errors and informing decisions. Preventing errors and informing decision in the early days of digital revolution, a significant portion of software applications graphical interface was taken up by dialogues and messages telling users what they did wrong or warning them about what their computer or software was unable to handle due to real or presumed technical limitations. The first edition of About Face was released during that time and was, as you can probably imagine, quite critical of this state of affairs. Today, the second of these categories of error messages has dropped by the wayside as a computational storage and communication speeds have all increased by several orders of magnitudes and as the sophistication of programming tools and techniques has similarly advanced. The first type of error message, scolding users for their mistakes, has begun to disappear as well, at least in consumer and mobile applications. Designers have discovered better way to eliminate errors before they happen, allow users to reverse their actions, and provide them with the almost magical ability to see the results of their actions before they even take them. Using rich, modeless feedback, most computers and increasingly many devices come with high-resolution displays and high-quality audio systems. Yet very few applications outside of games even scratch the surface of using these facilities to provide useful information about the app status, the user's task, and the system and its peripherals in general. So, the games actually did a lot of advantage or took a lot of advantage of the hardware improvement in high resolution displays and high quality audio system by providing useful information about the app modes or status, the user task, and the system and its peripherals in general. An entire toolbox is available to supply information to users. Unfortunately, actually a toolbox or these GUI capabilities are now available using these standard libraries or really just importing it from Node.js nowadays. Unfortunately, this means that subtle status information is simply never communicated to users because most designers know you don't want dialogues to pop up constantly, but constant feedback, especially positive feedback, is exactly what users need. In this section, we'll discuss how visual information, when displayed in a modeless fashion in the main views of application, won't stop the user flow and can all but eliminate those pesky dialogues. So rich visual modeless feedbacks, perhaps the most important type of modeless feedback is rich visual modeless feedback, RVMF. This type of feedback is rich in terms of giving in-depth information about the status or attributes of a process or object in the current application. So it actually provides the attributes or properties of the object in the current application in visual way. It is visual in that it makes idiomatic use of pixel on the screen, often dynamically. So it uses the pixel on the screen dynamically that makes it visual. It is modeless, like a pop-up or like a window box, modeless dialog box, in a sense that it is always readily displayed, requiring no special action or mode shift on the user's part to view and make sense of the feedback. For example, in Microsoft Outlook 2013, an icon next to an email sender's name visually indicates whether that person is available for a chat session or a phone call. So you see those in Facebook as well. The green icon shows that the user are active for a chat. So this is handy when a real-time conversation is preferable to an email exchange. This icon, as well as the ability to start a chat session from a right-click menu, means that users don't have to open their chat client and find the sender's name to see if that person is available. So basically, this icon as well this ability to start a chat session from a right-click menu means that users don't have to open their chat client, and another step is find the sender's name using search to see if that person is available. This is so easy and convenient that the user doesn't have to think about this. So another example of the strategy is designed for a Cooper client shown in figure 15.1. So this pane from a Cooper designed for a long-term healthcare information system is a good example of RVMF. The diagram represents all the rooms in the facility. Color coding indicates male, female, empty or mixed gender rooms. Numbers indicate empty beds, tiny boxes. Between rooms indicate shared bathrooms. Black triangles indicate health issues, and a tiny H means a health bed. This RVMF is supplemented with tooltips which show room numbers and occupant names and highlight any important notices about the room or its residents. A numeric summary of rooms, beds, and employees is given at the top. This display has a short learning curve. After mastering it, nurses and facility managers can understand their facility status at a glance. Here's another example, this time from iOS. When you download an app from the App Store, the downloading file appears on the home screen as an icon with a small dynamically updating progress indicator. So this actually small, it's actually a dynamically updating progress indicator in the back end, kind of like a video showing visually how far along the app is in the download and install process. So here, when apps are purchased from the Apple App Store, the app icon appears on the home screen of the iPad or iPhone, upper right. A dynamically updating circular indicator on the icon marks the progress of the download and install process. Sid Meier's Civilization, see figure 15.3. This game provides dozens of examples of RVMF in its main interface, which is a map of historical world. So here you are the leader of an evolving civilization that you are trying to build. Civilization uses RVMF to indicate half a dozen dynamically changing attributes of city. So it provides a dynamic change in attributes of the city. Let's make it all represented visually. If a city is more advanced, its architecture is more modern. So this architecture is more modern. If it's larger, the icon is larger and more embellished. If it's plagued by civil unrest, smoke rises from the city. Individual troop and civilian units also show status visually by way of tiny meters indicating unit health and strength. So the individual units are also shown visually using tiny meters indicating their health, could be green or red. So if it's civil unrest, there's a smoke. There will be a smoke like this. Even the landscape has RVMF. Dotted lines marking spheres of influence shifts as unit move and cities grow. So there's a dotted lines marking spheres of influence. It will shift as you move. So here, dotted lines of influence means you're only covering this circle. Although terrain changes as roads are laid, forests are cleared, and mountains are mined. So as roads are laid, forests are cleared, and mountains are mined. Although dialogue exists in the game, much of the information needed to understand what is going on is communicated clearly with no words or dialogue whatsoever. So here, Civilization is a game in which you can chart the course of civilization. Its interface provides dozens of examples of rich visual models feedback. So imagine all the objects that had pertinent status information on your desktop or in your application could display their status in this manner. Printer icons could show how close the printer is to completing your print job. Icons for hard drives and removable media could show how full these items are. When an object is selected for drag and drop, all the places that could receive it would become highlighted to announce their receptiveness. So when an object is selected for drag and drop, all the objects that could be available for drop will show like what we discussed in the previous video. Think about the objects in your application and their attributes, especially dynamically changing ones, and what kind of status information is critical for users. So you need to find the critical mode, shift, and status in your application, and then make sure to provide visual rich models feedback for that. Figure out how to create a representation of this. After the user notices and learns this representation, it tells him what is going on at a glance. There should always be a way to get full detailed information if the user wants it, such as in here in scroll bar. You can see the full details when you look at the settings on what page you are. But this visual should be enough in most cases. Put this information into main application windows in the form of RVMF and see how many dialogues you can eliminate from routine use. So you need to put that information into the main application window in the form of RBMF and see how many dialogues you can eliminate from routine use using those visual modus feedback using trial and error. One important point needs to be made about rich modus visual feedback. It isn't for beginners. Even if you add tooltips to textually describe the details of any visual cues you add, which you should, a tooltip requires user to perform work to discover it and decode its meaning. So it's not for beginners. Even if you add the tooltips, the user will need to textually decode it first before he can know what that symbolize next time. Kind of like reading allows you to have a symbolic or remember the meaning without actually looking at it. It's the same thing with this rich modus feedback. You need to learn it first. So to textually describe the details of any visual cues you add, which you should, a tooltip requires user to perform work to discover it and decode its meaning. RVMF is something that users will begin to use over time. When they do, they'll think it's amazing, but in the meantime, they will need the support of menus and dialogues to find what they are looking for. This means that RVMF, used to replace alerts and warnings of serious trouble, must be extraordinarily clear to users. Make sure that this kind of status is visually emphasized over less critical. So we need to use the visual design principle again in this visual representation. More informational RVMF. The clerk can then use his sense of hearing to monitor the success of his inputs while he keeps his eye on the documents. So another thing that you could use is the hearing senses, which we will discuss next. So again, in the previous book, we will discuss how visual is the most cognitively demanding and hearing is the next. So we will provide this in case of the user is not able to uh, identify, wants to provide confirmation visually. Audible feedback in the data entry environments, clerks sit for hours in front of computer screens entering data. These users may well be examining source documents and typing by touch instead of looking at the screen. If a clerk enters something erroneous, he needs to be informed of it via both auditory and visual feedback. The kind of auditory feedback we're proposing is not the same as the beep that accompanies an error message box. In fact, it isn't a beep at all. The auditory indicator we propose as feedback for a problem is silence. Avoid negative audible feedback. Despite the fact that Microsoft and Apple have tried to improve the quality of alert sounds by hiring sound designers, including the legendary Brian Eno for Windows 95, warm ambience doesn't change the fact that sounds are used to convey negative, often insulting messages. On most systems, error dialogues normally are accompanied by a shrill beep, so audible feedback has become strongly associated with them. That beep is a public announcement of the user's failure. It explains to all within earshot that you have done something stupid. It is such a hateful idiom that most software developers now have unquestioned belief that audible feedback is inappropriate to interface design. Nothing could be further from the truth. It is the negative aspect of the feedback that presents problems, not the audible aspect. Negative audible aspect has several things working against it. Because the negative feedback is issued when a problem is discovered, it naturally takes on the characteristic of a home alarm. Unfortunately, users are constantly doing things that cause apps to generate error message, so these noises have become part of the normal course of interaction. Unfortunately, users are constantly doing things that cause apps to generate error message. So these noises have become part of the normal course of interactions. Alarms have no place in this normal relationship. Provide positive audible feedback. Almost every object and system outside the world of software offers sound to indicate success rather than failure. When we close the door, we know that it is latched when we hear the click, but silence tells us that it is not yet secure. When we converse with someone and she says yes or ha, we know that at least minimally she registered what was said. When we turn the key in our car's ignition and get silence, we know we have a problem. When success with our tools yields a sound, it is called positive audible feedback. Our software tools are mostly silent. All we hear is the quiet clicks of the keyboard. Hey, that's positive audible feedback. Every time you press a key, you hear a faint but positive sound. Keyboard manufacturers could make perfectly silent keyboards, but they don't because we depend on audible feedback to tell us how we are doing. This is one of the reasons why tablet computers like the iPad provide audible feedback for their touchscreen keyboards by default. The feedback doesn't have to be sophisticated. Those clicks don't tell us much, but they must be consistent. The true value of positive audible feedback is that its absence is an extremely effective problem indicator. The effectiveness of positive audible feedback originates in human sensitivity. Nobody likes to be told that they have failed. Error message boxes are negative feedback, telling the user that he has done something wrong. Silence can ensure that user know this without actually being told of the failure. Our software should give us constant, small, audible cues just like our keyboards.
Our applications would be much friendlier and easier to use if they issued barely audible but easily identifiable sounds when the user actions are correct. The app could issue a reassuring click every time the user enters valid input into a field and an affirming tone when the form has been successfully completed. If an application doesn't understand some input, it should remain silent, subtly informing the user of the problem, allowing her to correct the input without embarrassment or ego bruising. When the user drags and drops an object appropriately, he might be rewarded with a soft, cheerful plunk from the speaker for success or with silence and a visual hop back to its origin point if the drop was not meaningful. As with visual feedback, computer games tend to excel at positive audio feedback. Apple OS X also does a good job with subtle positive audio feedback for activities like document saves and drag and drop. Of course, the audible feedback must be at the right volume for the situation. Windows and the Mac offer a standard volume control. So one obstacle to beneficial audible feedback has been overcome. So Windows and Mac's operating system has a standard volume control that control the application sound compared to other apps in the system. But audible feedback should not overpower music playing on the computer. That's why even if you have multiple songs, it doesn't disrupt the system. Replacing annoying useless dialogues with subtle and powerful modeless communication can make the difference between an app user will despise and one they will love. Think of all the ways you might improve your own applications and prevent user errors with RVMF and other mechanism of modest feedback. Undo, redo, and reversible histories. Undo is the remarkable facility that let us reverse a previous action, painlessly turning back the clock on our mistakes. Undo is critically important for users, but it's not quite as simple as it may appear at first glance. Undo should follow mental models. Undo is traditionally thought of as the rescuer of users in distress, the knight in shining armor, the cavalry galloping over the ridge, the superhero sweeping in at the last second. As a computational facility, Undo has no merit because they don't make mistakes. Computers have no need for undo. Human beings, on the other hand, make mistakes all the time, and Undo is a facility that exists for their exclusive use. This singular observation should immediately tell us that all of the facilities in an app Undo should be modeled the least like its construction methods, its implementation model, and the most like the user's mental model. So these are the mental model or the one of the function that should be prioritized that will be closest to the user's mental model. From a human standpoint, they are perfectly normal. Human mistakes are so commonplace that if you think of them as errors or even as abnormal behavior, you will adversely affect the design of your software. User mental model of mistakes. Users generally don't believe, or at least don't want to believe, that they make mistakes. Following a persona's mental model means absolving him of blame. The implementation model, however, is based on an error-free CPU. So if we follow the mental model of the persona, they should not be blamed because what they think is right. So the user must come first. The solution is for the user interface designer to abandon the idea that the user can make a mistake. This means that everything the user does is something he or she considered to be valid and reasonable. Most people don't like to admit to mistakes in their own mind, so the app shouldn't contradict this mindset in its interactions with users. Undo enables exploration. If we abandon the implementation model, we kiss to imagine the user as a module of code or peripheral that drives the computer, and we begin to imagine him as an explorer, proving the unknown. We understand that exploration involves inevitable forays into blind alleys and down dead ends, so we should treat this as an exploration for the user to learn the interface instead of treating them like a computer. It is natural for humans to experiment, to vary their actions, to probe gently against the veil of the unknown to see where their boundaries lie. How can they know what they can do with the tool unless they experiment with it? Of course, the degree of willingness to experiment varies widely from person to person, but most people experiment at least a little bit. An application can either rebuff those perceived mistakes or assist users in their application. So an application could return that mistake, or they can assist them in the exploration. So you choose your battle. Undo is thus a primary tool for supporting exploration in software user interfaces. A significant benefit of undo is purely psychological. It reassures users it is much easier to enter a cave if you are confident that you can get back out of it anytime. The undo function is that comforting rope ladder to the surface, supporting the user's willingness to explore further by assuring him that he can back out of any dead-end caverns. Curiously, users often don't think about undo until they need it, much of the same way that homeowners don't think about their insurance policies until disaster strikes. Users frequently charge into the cave half prepared and start looking for the rope ladder for undo only when they encounter trouble. Designing an undo facility, although users need undo, it doesn't directly support any particular goal that underlies their task. Rather, it supports a necessary condition, trustworthiness on the way to a real goal. Users visualize the undo facility in different ways depending on the situation and their expectation. If a user is very computer naive, he might see it as an unconditional panic button for extricating himself from a hopelessly tangled misadventure. A more experienced computer user might visualize undo as a storage facility for deleted data. So undo could be a storage on this inside the directory of the file that could use kind of like a recycle bin. A really computer sympathetic user with a logical mind may see it as a stock of procedures that can be undone one at a time in reverse order. To create an effective undo facility, we must satisfy as many of these mental models as we expect our personas will bring to bear. The secret to designing a successful undo system is to make sure that it supports typically used tools and avoids any hint that undo signals, whether visually, audibly, or textually, a failure by the user. So the secret here is the support or using this undo function and then visual rich modulus feedback on the most common use function. Whether visually, audibly, or textually, such as Control Z, a failure by the users. Errors are generally single, incorrect actions. Exploration, by contrast, is a long user series of probes and steps. So, exploration by contrast, if the user are exploring our software, he will do so in a series of steps, and some of which are keepers and some of which must be abandoned. Undo works best as a global up-wide function that undoes the last action, regardless of whether it was done by direct manipulation or through a dialogue. So whether it's through a
accelerators, direct manipulation through click or touch, or through a dialog, it must be able to do so using a global undo function. One of the biggest problems in current implementations of undo functionality is when users lose the ability to reverse their actions after they save the document in Excel, for example. So one of the biggest implementation problem is undo functionality is user lose the ability to reverse their action after they save the document, which should not be. After they save it, they should still be able to undo, just like in Word, Microsoft Word. Just because the user has saved her work to avoid losing it in a crash doesn't necessarily mean that she wants to commit to all the changes she has made. Furthermore, with our large disk drives, there's no reason to save the undo buffer. There's no reason not to save the undo buffer with the document. So actually, what we do is this undo is just a buffer or a copy of the document, which we will later see in memory, that saves it. Users have a difficult. It's like a version control system that save every snapshot of what we save in the memory. Uh, Undo can also be problematic for documents with embedded objects. If the user makes changes to a spreadsheet embedded in a Word document, clicks the Word document, and then invokes undo, the most recent Word action is undone instead of the most recent spreadsheet action. So since you click the Word document, but then you want to undo the action you did on the spreadsheet, the one you did in the Word will be undone. So users have a difficult time with this. It forces them to abandon their mental models of a single unified document and forces them to think in terms of implementation model. One document is embedded within another, and each has a separate editor with a separate undo buffer. So it has a separate editor and undo buffer in memory, which confuse users. So common types of undo, as is common in the world of software, there is no adequate terminology to describe different types of undo. They are uniformly referred to as undo and left at that. This language gap contributes to the lack of innovation in producing new and better variants of undo. In this section, we define several undo variants and explain their differences. Incremental and procedural actions. Undo operates on the user's actions. So these are the single undo. A typical user action in a typical application has a procedural component. So a typical action is a procedural component, what user did, and often a data component, what information was affected by that function or procedure. When the user requests an undo function, the procedure component of the action is reversed. Or the function, when undo function are done, the procedure component of that function to that data is reversed. If the action had the data component resulting in the addition, modification, or deletion of data, that data is modified appropriately. If it was deleted, it will go back. Cutting, pasting, drawing, typing, and deleting are all actions or functions or procedure that have a data component. So undoing them involves removing or replacing the affected text or image parts. Actions that include a data component are called incremental actions. Many undoable actions are data-free transformation, such as paragraph reformatting operation. You're not actually
that action does not include a data component. So undoing it is data-free transformation. So these data-free transformations, such as paragraph reformatting operation or function in a word processor or a rotation in a drawing app. Both of these operations act on data, but neither of them adds, modifies, or delete data. So they act data, they format it, but neither of them change the data in the database. It doesn't edit it, or it doesn't delete, it doesn't add something on the database. Actions like this with only a procedure component are procedural actions. It's not incremental action. Most existing undo functions don't discriminate between procedural and incremental actions. They treat it the same. So when you undo, you're undoing those same actions, but simply reverse the most recent actions. Blind and explanatory undo. Normally, undo is invoked by a menu item or toolbar control. So it's not Control Z, it's usually an icon in a menu or text or a toolbar control in the drawing application or any application. But for Word, they have accelerators. Users know that triggering the idiom undoes the last operation or function, but there is no indication of what that operation is. This is called blind undo. On the other hand, if the idiom includes a textual or visual description of that particular operation that will be undone, it is an explanatory undo. So if there's a visual description or like a tooltip, that is called explanatory undo. Sometimes it's just an icon or menu item, which is a blind undo. For example, if the user's last operation was to type the word design, the undo function on the menu says undo typing design, explanatory undo. So there is a rich modulus feedback. It's generally a much more pleasant feature than blind undo because you don't know that you have reversed the operation. It is fairly easy to put on a menu item, but it is more difficult to put on a toolbar control. So it's easy to put it in a menu item just like in any other dialogues, but putting it as an icon is more difficult because the user needs to learn it, although putting the explanation in a tooltip is a good compromise. Single and multiple undo. The two most familiar types of undo in common use today are single undo and multiple undo. Single undo is the most basic variant, reversing the effects of the most recent user action, whether procedural or incremental. Performing a single undo twice usually undoes the undo and brings the system back to the state it was in before the first undo was activated. This is by far the most frequently implemented undo in applications and certainly adequate, if not optimal, for many applications. So a lot of applications could benefit from this, but not most, though most applications implement this type of undo. Multiple undo can be performed repeatedly in succession. It can undo more than one previous operation in reverse temporal order, a reversible history. Any app with symbol undo must remember the user's last operation or last function or procedure in its stock in memory. And if applicable, cache any change data. So if applicable, you can use the new technology which is cache in memory to be able to revert to that version quickly. If the application implements multiple undo, it must maintain a stack of operation or stack of procedure functions that the user does. And then that action or operation
could have a data and just a procedure inside it, just a procedure or an increment function. The depth of which the user may set as an advanced preference in the dialog settings. Each time undo is invoked, it performs an incremental undo. It reverses the most recent operation, replacing or removing data as necessary and discarding the restored operation from the stack. Limitation of single undo. This problem crops up when the user don't notice his mistake immediately. For example, assume he deletes 6 paragraphs of text and then deletes one word, and then decides that the 6 paragraphs were erroneously deleted and should be replaced. Unfortunately, performing undo now merely bring back the one word and the 6 paragraphs are lost forever. In some applications, any click of the mouse, however innocent of function it might be, causes the single undo function to forget the last meaningful thing the user did. Although multiple undo So actually some application, a click of a mouse are registered as an action. So if you undo it, it causes the single undo function to forget the last meaning the user did, or the actual action. Although multiple undo solves this problem, it introduces some significant problem of its own. Limitations of multiple undo. The solution to single undo has been to create a multiple level implementation of the same incremental undo. The application saves each action the user take. So actually the solution to single undo is to create multiple implementation or multiple function that will save that incremental undo. And then the application will save each that procedure the user takes. When the user selects undo repeatedly, each action is undone in the reverse order of its original invocation of that action or function. In the example given in the preceding section, the user can restore the deleted word with the first invocation of undo and restore the precious 6 paragraphs with the second invocation. Having to redundantly redelete the single word is a small price to pay for being able to recover those 6 valuable paragraphs. But this doesn't change the fact that undo mechanism is built on faulty model, and in other circumstances, undoing function in a strict LIFO, last in, first out order can make the cure as painful as the disease. Imagine again our user deleting 6 paragraphs of text, calling up another document, and performing a global find replace. So if you want to just delete or go back to the 6 paragraph, you also need to undone this global find and replace function, which takes a lot of effort. Now this time, the intervening operation was not the insignificant single word deletion of the earlier example. The intervening operation was complex and difficult, and having to undo it is clearly an unpleasant excision effort. So it's an exercise. It would sure to be nice to be able to choose which operation in the queue to undo and to be able to leave intervening but valid operations untouched. The problem with multiple undo are not so much due to its behavior as much as they are due to its representation. Most undo facilities are constructed in an unrelentingly function-centric manner. They remember what the user does function by function and separate her action by individual function. So that's greatest easy for developer, that's also its greatest weakness. In the time-honored way of creating represented models, In a time-honored way of creating represented models that follow implementation models, undo system tend to model code and data structures or the data structures of that procedure in the stock and the array of the memory instead of user goals. Each click of the undo button reverses precisely one function size byte of data structure if it's an incremental action of behavior. Reversing on function by function basis is an appropriate mental model for solving most simple problems that arise when the user makes an erroneous entry. However, when the problem grows more convoluted, the incremental multiple step undo model doesn't scale very well. Undo and redo. So the redo function came into being as the result of the implementation model for undo, wherein operations must be undone in reverse sequence. So because of that implementation model of undo, you can easily actually do this function in the back end. Redo essentially undoes undo and is easy to implement if developers have already gone to the effort of implementing undo function with rich model feedback and access modifiers such as control Y. Redo prevents a diabolic situation in multiple undo. If the user wants to back out of a sequence of actions, he clicks the undo control a few times, waiting to see things return to the desired state. Many applications that implement single undo treat the last undone action as undoable action. In effect, this makes a second invocation of the undo function a minimal redo function. So the way to actually implement this redo function is to treat the last undone action as an undoable function. In effect, this makes a second invocation of the undo function a minimal redo function, which makes you to redo the function. Group multiple undo. Microsoft Word contains what has unfortunately become a somewhat typical facility, a variation of multiple undo that we'll call group multiple undo. Group multiple undo. It has several levels showing a textual description of each operation in the undo stock. So you can examine the list of past operations and select an operation in the list to undo. So here's the picture. However, you're not undoing that one operation, but rather all the operations back to that point, such as here, formatting italic until typing. So all the operation including formatting and italic is included. This style of multiple undo is also employed by many Adobe products. As a result, you cannot recover your 6 missing paragraphs without first reversing all the intervening operations. So figure 15.4, with Microsoft Office undo or redo facility, you can undo multiple actions, but only as a group. You can choose to undo only the thing you did 3 actions ago. Redo works in the same manner. After you select one or more operations to undo, the list of undone operations becomes available in reverse order in the redo control. So after you select one or more operations in the stock, you can then go back using redo. Redo works exactly the same way as undo. You can select as many operations to redo as you want. So you can redo, or what I do here is I copy and paste the paragraph that I missed in the last 3 stock operations in the stock, and then I go back to the latest version and just copy and paste that from my notepad. So you can select as many operations to redo as you want, and all operations up to that specific one are redone. The applications offer 2 visual cues to this fact. If the user selects the 5th item in the list, that item and all 4 items before it in the list are selected. Also, the text legend says undo 5 actions. So there's 2 visual feedback.
The fact that designers had to add that text legend tell us that regardless of how developers constructed it, the users were applying a different mental model. So even if there's a rich visual models feedback, since the user are applying different mental model, this RVM app did not work. The users imagined that they could go down the list and select a single action from that pass to undo. The app didn't offer that option. So this is like a door with a pull handle that has push shine, which everybody still pulls on anyway. While multiple undo is certainly a very useful mechanism, there's no reason not to finish the job, and are ample computing resources to allow users to undo just the undesirable action. Other types of undo. Undo in its simplest form, single undo, conforms to the user's mental model. I just did something I now wish I hadn't. I want to click a button and undo the last thing I did. Unfortunately, this represented model rapidly diverges from the user's mental model as the complexity of the situation grows. In this section, we discuss models of undo-like behavior that work a bit differently from the more standard undo and redo idioms. This continuous multiple undo. Some users often take several complex steps into the unknown before realizing that he is lost and needs to get a bearing on the known territory. At this point, however, he may have performed several interlaced functions, only some of which are undesirable. So some of which are undesirable and he doesn't know which is which. He may want to keep some actions and nullify others. So he may want to do some functions on the stack and want to discard other, not necessarily in strict reverse order. What if he entered some text, edited it, and then decided to undo the entry of that text but not undo the editing of it? Such an operation is problematic to implement and explain. In this more complex situation, the simplistic representation of undo and as a single leaf, a stock, doesn't satisfy the way it does in simpler situations. The user may want to study his action as a menu and choose a discontinuous subset of them for reversion while keeping others, such as hitting control and click for those menu or stack of operations in the menu that he wants to remove. This demands an explanatory undo with a more robust presentation that might otherwise be necessary for a normal blind multiple undo. Additionally, the means of for selecting from that presentation must be more sophisticated, representing the operation in the queue to show the user what he is actually undoing is more difficult problem. So representing the functions in the queue to show based on the user mental model what is actually undoing is more difficult problem, especially for user that does not have the implementation model thinking like developer. So this demands an explanatory undo with a more robust representation. So like a tooltip and robust explanation to the user that might otherwise be necessary for a normal blind multiple undo. So since you're sometimes just doing blind undo, if you implement this kind of stuff, it may be hard to implement in back end and the front end. Category specific undo. Backspace is a classic example of an incremental undo, reversing only some data while ignoring other intervening actions. Yet, if you imagine an undo facility that had pointer that could be moved and that could undo the last function that occurred where the pointer points, you probably think that such a feature would be patently unmanageable and would confuse a typical user. But thankfully it's not, because it became a learned behavior by clicking and then backspacing the especially for discontinuous data. We like what I've said earlier, if you want to go back and then just get back the previous paragraph, you just control Z on the 5 step and just copy that
paragraph that you need. If the user mistypes something and then performs an unrelated function such as paragraph formatting and then presses the backspace key repeatedly, the mistyped characters are erased and the formatting operations is ignored. So it doesn't undo the formatting, just the one he chose. Depending on how you look at it, uh, this can be great flexible advantage, allowing users to undo discontiguously at any selected location. You could also see it as a trap for users because they can move the cursor and inadvertently backspace away characters that were not the last ones keyed in. Logic says that this latter case is a problem. Empirical observation says that it's really a problem for users. Such discontinuous incremental undo, so hard to explain in words, is so natural and easy to use because everything is visible. Users can clearly see what will be backspace away. Experience tells us that backspace does nothing of the sort. It works as well as it does because its behavior is consistent with the user's mental model of the cursor. Because it is the source of added characters, it can also reasonably be the locus of deleted characters. So it's like pointing an object in a drawing and then backspacing what's the recently undo on that drawing. Or in this case, if it is contagious data application, removing that specific word or sentence. Generated from this, we could perhaps create a different categories of incremental undo, like a format undo function that would undo only previous format commands and other types of category specific undo actions. If the user entered some text, change it to italic, entered some more text, increase the paragraph indentation, entered some more text and then click the format undo button, only the indentation increase would be undone if you have categorized the undo in this indentation, italic, or specific commands. A second click of the format undo button would reverse the italic operation. Neither invocation of the format undo would affect the content. What are the implications of category-specific undo in a non-text application? A drawing app, for example, could have a separate undo commands for pigment application tools, transformations, and cut and paste. There's really no reason that we couldn't have independent undo function for each particular class of operation. So there's no reason for that class because you could divide that in the classes in the back end. Pigment application tools include all drawing implements, pencils, pens, fills, sprayers, brushes, and all shape tools, rectangles, lines, ellipses, arrows. Transformations include all image manipulation tools. Shear, sharpness, hue, rotate, contrast, and line weight could all be categorized, and backspace are allowed to undo those based on those categories. Cut and paste tools include all lassos, marks, clones, drags, and other repositioning tools. Unlike the backspace function in the word processor, undoing a pigment application in a drawing app would be temporal and would work independently of selection. That is, pigment that is removed first would be the last pigment applied. So you can apply LIFO in specific categories and objects regardless of the current selection. Western text has implied reading order from the upper left to the lower right. Deleting from the lower right to the upper left maps to a strong intrinsic mental model, so it seems natural. In a drawing, no such conventional order exists, so any deletion order other than the one based on entry sequence would be disconcerting to users. A better alternative might be to undo within the current selection only. The user select a graphic object, for example, and request a transformation undo. The last transformation to have been applied to the selected object would be reversed. Most software users are familiar with incremental undo and would find a category-specific undo novel and possibly disturbing. However, the ubiquity of the backspace key shows that incremental undo is a learned behavior that users find helpful. If more apps had modal undo tools, users would soon uh, adapt to them. So if they have modal undo like this, they will adapt. They would even come to expect them the way they expect to find a backspace key on word processors. Deleted data on buffers or memory. As the user works on a document for an extended time, she may want a repository of deleted text. Consider 6 missing paragraphs. If they can be as difficult to reclaim through undo as they are to rekey, our users is thinking if the app would just remember the stuff I deleted and keep it in a special place, I could get what I want directly. The user is imagining a repository of the data components of her actions rather than a merely a LIFO stack of functions. So it's kind of just stack of functions in memory, a deleted data buffer, uh, which is a repository of data components of her actions. The users want the missing text without regard to which function got rid of it. So whether it's Control Z, backspace, etc. The usual manifest model forces her not only to be aware of every intermediate step, but also to reverse each one in turn. To create a facility more amendable to our user, we can create, in addition to the normal undo stack, an independent buffer that collects all deleted text or data. So the current undo model forces her to remember every intermediate step, which is not ideal. To create a facility more amendable to our user, we can create, in addition to the normal undo stack, an independent buffer that collects all deleted text or data. At any time, she can open this buffer as a document and use standard cut and paste or click and drag idioms to examine and recover that desired text. It's like version control, which we will discuss later. If the entries in this deletion buffer were headed with simple data stamps and document names, navigation would be simple and visual. The user can browse the buffer of deleted data at will, randomly rather than sequentially. Finding those 6 missing paragraphs would be simple, visual procedure, regardless of the number or type of complex intervening steps the user had taken. The data must be saved in a buffer anyway, so this feature would be quite useful in most applications, whether spreadsheet, drawing up, word processor, or inverse generator. Versioning and reversion. Users occasionally want to back up long distances, but when they do, the granular actions are not terrifically important because it's just stack of operations in queue at that time in memory. So versioning, as we discussed in chapter 14, simply makes a copy of the entire document the way a camera snapshot captures an image in time. Because versioning invokes the entire document, it is typically implemented by direct use of the file system. So because it's a snapshot, an image in time, it involves entire document. It is typically involve a file system, or kind of like a file manager we have in Windows. The biggest difference between versioning and other undo system is that the user must explicitly request the version, recording a copy or snapshot of the document. If he later decides that these changes were undesirable, he can return to the saved copy a previous version of the document, kind of like really a version tool in GitHub. Many tools exist to support the versioning concept in source code, but this concept is just emerging in the world outside of software development. So here, Google Docs allows multiple people to collaborate on a single document. There's a timestamp. It creates a new version every time the user changes to the documents and allow users to view the different versions. This can be quite useful because it allows collaboration without worry that valuable work will be overwritten. This should include some information about each document, such as the time and date was recorded, the name of the person who recorded it, the size, and some optional user-entered notes. A user should be able to understand the differences among versions and ultimately choose to revert to any of those versions. Just a moment, guys. I just cook my rice. Right, so let's continue. So here this should include some information about each document, such as time and date was recorded, the name of the person who recorded it by signing in on the word first, and the size, and some optional user entered notes that you can put on that, like in GitHub, in pushing it. Freezing involves locking selected data within the document so that it cannot be changed, and anything that has already been entered becomes uneditable. So it's kind of like in Word, you're making it uneditable when you're using it to create presentation like this. Although new data can be added, but you can also configure it to add new data. Existing paragraphs are untouchable, but new ones can be added between older ones. So kind of like a version system as well, but you're freezing the current so that it can't be added, but you can be edited, but you could add to it. So this is much more useful for a graphic documents than for a text document. So it's much like an artist spraying a drawing with a fixative. So like an artist don't want to spray the previous one that's already solid. It could use this type of functions or feature. All marks made up to that point are now permanent, yet new marks can be made at will. Images already placed on the screen are locked down and cannot be changed. But new images can be freely superimposed on the older ones. Undoing the undoable. Some operations simply cannot be undone because they involve some action that triggers device not under the application direct control. So because the application could control some files that is not direct control, it cannot do something. For example, after an email message has been sent, there's no undoing it. So Gmail gives you a short amount of time to halt an email by not actually sending it for a few seconds after you click send. So you can provide this feature. This also rich modeless feedback that allows you to support this feature. Sometimes, in case of financial and medical transactions, undo is an appropriate function. But you can still better support human goals and mental models by providing a way to reverse or adjust the action while leaving an audit trail. So you don't need to reverse the action, but you can audit the trail. So spend some time looking at your own application and see if you can find functions that seem as if they should be undoable, but currently aren't. So look at the function in your application, especially the most useful one that is undoable, but could be undone, because it will definitely help to provide a rich experience to the
customer. You may be surprised by how many you find. So what if compare and preview? Besides providing robust support for terminally indecisive, the paired undo redo function is a convenient comparison tool. Suppose you want to compare the visual effect of rag right margins versus justified right margins. You start with rag right and then invoke justification. Then you invoke undo to see rag right. Then you invoke redo to see justified margins again. In effect, toggling between undo and redo implements a comparison or what if functions. It just happens to be represented in the form of its implementation model. If this same function were added to the interface following a user's mental model, it might be represented as a comparison or what if control. This function would let you compare several states before confirming action, kind of like undo redo or comparison feature that has a name in itself for you to see what future may look like, such as a preview icon in Windows that allows you to see what the printed copy look like. Some TV remote controls include a jump button that switches between the current channel and previous channel. So it's kind of like undo and redo. Very convenient for viewing two programs concurrently. So those channels are actually two programs in the backend. The jump function provides the same utility as the undo redo function, pair with a single command. So the jump actually is paired undo and redo in a single command. So a 50% reduction in exercise for the same functionality. So you don't need to do two accelerators or commands for that. When used as comparison function, undo and redo are really one function and not two. One says apply this change and the other says don't apply this change. A single compare button might more accurately represent the action to users. Although we have been describing this tool in the context of a text-oriented word processing app, a compare function might be most useful in an image processing or drawing application, where users apply successive visual transformation. The ability to see the image with transformation or even multiple variants of it simultaneously and quickly and easily compare it to the image without the transformation would be great help to the digital artist. Many products address this with thumbnail so that you can see that in a picture or little picture that allows you to quickly and easily compare it. So it's not actually just useful in Word, it also more useful in image application. Many products address this with thumbnail preview image as shown in figure 15.7, so you can see what it will look like. Number photo processing apps on the iPad including Photo Toaster provide preview thumbnails of the image you are working on, each showing the result of a different effect or image parameter change. Tapping the thumbnail applies the change to the image, which in itself a sort of preview since it can't be undone with a single action tap. Compare may seem like an advanced function, and it is for some applications. Just as the jump function may not be used by the majority of TV watchers, the compare button would remain a nicety for frequent users. This shouldn't detract from its usefulness, however, and for some applications like photo manipulation and other media authoring app, visual comparison tools that show the future before it happens have become almost a necessity. Again guys, thank you for watching. See you on the next video. Peace.